Good day, everyone. I am Trisha Lazo from the BSMS Biological Engineering Program under the supervision of my thesis advisor, Dr. Lemmuel, and today I will be presenting my study, which is achieving antibiofouling on microporous membranes prepared with the green solvent via spraying an aqueous antifouling copolymer solution. To begin with, I would like to discuss to you the applications of membranes. So how are they applied? They are applied in some of the following areas such as wastewater treatment, desalination, gas separation, and hemodialysis. Now, I want to emphasize on wastewater treatment and desalination because these fields directly contribute to clean water and sanitation, or the goals of SDG 6, which is to ensure availability and sustainable management of water and sanitation for all, especially since there has been a scarcity on clean water for human life, no? And however, there are problems when it came to the production of membranes. The solvents that we use in membrane production are dimethyl acetamide, DMAC, dimethyl formamide, DMF, and N-methyl 2-pyrrolidone, or NMP, and these solvents were found to be toxic. They are harmful to aquatic life and due to the traces that are found in water, in underground water or in water systems, and they are found to be toxic to the reproductive health of humans. And so the use of these solvents have been banned or restricted as of late, especially by the European Union, since they are known to be toxic. So because of this, it is not sustainable, and it is not in accordance to the SDG 12 of the current SDG goals, which is responsible consumption and production. Well, although it is able to provide clean water, the process of creating a membrane or fabricating a membrane is not at all sustainable. So the goal of this study is to contribute to SDG 12, responsible consumption and production of membranes, and to improve clean improve clean water provisions from wastewater treatment. So with that, to accomplish these goals, we've researched on a number of green solvents, and among them are styrene, triethyl phosphate, gamma valerolactone, dimethyl sulfoxide, and gamma butyrolactone. And these solvents are characterized by their low volatility, low flammability. They are renewable, especially with gamma valerolactone, because it was found to be produced using biomass. It is the same also for serine. It has low toxicity and biodegradable, therefore are good substitutes to the traditional organic solvents now. So the objectives of the study, in order to contribute to the SDG 12 and to in wastewater treatment in general, and the current movement in creating more sustainable production of membranes, is to, one, fabricate and modify green membranes and characterize their physicochemical properties. Two is to assess the membrane's biofouling performance using static fouling resistance tests and evaluation of biofouling and bacterial rejection in wastewater. And in here, we will simulate a wastewater treatment through a dead-end filtration. Now, in order to produce the antifouling copolymer, we use polystyrene and polyethylene glycomethacrylate. This will serve as the antifouling unit, and this will serve as the anchoring unit in order to stabilize the amphiphilic polymer. So because polystyrene or polyethylene glycomethacrylate is an amphiphilic polymer, no? And we use a 30 to 70 ratio of polystyrene and polyethylene glycomethacrylate because this was found to be the most effective in antifouling, even within a random configuration as well, because it is more effective than a block configuration, no? And these polymers were dissolved in solvent, and we use an AIBN initiator in order to synthesize polystyrene or polyethylene glycomethacrylate, or PSR pegma. We analyze the structure of PSR pegma in order to confirm it, and we use HNMR and FTIR spectroscopy. Now, as you can see from the structure of PSR pegma in this picture, the characteristic peaks can be found in HNMR for this group and these groups. The C double bond, the characteristic peaks as well from the FTIR spectroscopy can also be found in the FTIR spectra for PSR pegma, thus confirming that we did synthesize the PSR pegma. Then we prepared the casting solution or the green membranes by dissolving 10% PVDF in GBL, stirred for 6 to 8 hours at 100 RPM and a dissolution temperature of 50 degrees Celsius. The membrane was fabricated using Lips process or liquid-induced phase separation. Now, in here we used a casting knife with a thickness of 300 microns, and it is very important that the casting solution during casting is at 50 degrees Celsius or else it will gel. We use a dual bath coagulation method in order to produce bicontinuous porous structures and a pore size within the microfiltration, as is the goal of the study is to produce membranes within the microfiltration unit, within the microfiltration range. And after casting with the casting knife, the glass plate was immersed in ethanol for 15 seconds and immersed in the eye water for the next 24 hours. We evaluated the membrane morphology using SEM, and as you could see from the structures in the cross-section, the pores are indeed interconnected or they are bicontinuous. Interconnected pores are highly important in order to increase the flux and basically the efficiency of the membrane when it comes to wastewater treatment. And the interconnected pores will allow a higher flux compared to other structures. So we also evaluated the bulk porosity and mean pore size of the membranes, and all of it falls above 0.4 microns, which is fit for microfiltration since the diameter of bacteria usually falls above 0.4 microns as well. And the bulk porosity remains at 70, especially for these membranes, no? It is highly porous at more than 70%, indicating that the membrane has a good structure and is porous. We also coated or modified the surface of the membrane, and these are the following coating solution concentration with the spray coating, with the automatic spray coating equipment. 5, 10, 15 were the coating solution concentration, and these are their sample IDs. And we use an operating pressure of 0.1 atmosphere and a scan rate of 3000 millimeter per minute. We analyzed the surface of each membrane and through FTIR and FTIR mapping. So for both the top and bottom surface, in order to confirm whether the membrane was modified, or whether the bulk of the membrane was modified, and found characteristic peaks at C double bond O from the EGMA group, from the EGMA, and from the pegma portion of the membrane of the copolymer in both the top and bottom surface, indicating that the membranes were indeed modified, not just the top but also the bottom surface, despite only exposing one surface to the membrane. We use FTIR mapping in order to confirm the uniformity of the coating, and found that PVDF10 had the most uniform coating compared to PVDF15 and 20, despite having more concentrations of the antifouling copolymer unit. And later on, I will discuss the relevance of this uniformity when it comes to coating. We analyzed the surface chemistry using XPS and found characteristic peaks for the PS pegma in PVDF10, which is not visible in the pristine PVDF now. Then we analyzed membrane wettability and found PVDF10 had the greatest membrane wettability, or had the highest hydrophilicity compared to 15 and 20, despite having a greater concentration of the antifouling copolymer. Although hydration capacity for PVDF15 is higher than PVDF10, but PVDF10 is very, very close when it comes to hydration capacity to PVDF15. Now, this is possible because of aggregation, as you could see, uh, and I will discuss this later on. No? And we also did protein absorption test for static antifouling and found that PVDF10 had the greatest resistance when it came to fouling by mapping FTIR mapping analysis at 1650 at a wave number of 1650, which is characteristic for BSA. And this is very important, no, because although PVDF15 and 20 had greater antifouling copolymer units from their increased concentration, PVDF10 had the least attachment because of, again, the uniformity of the PVDF's coating compared to PVDF10 and 20. Now, we suspect that aggregates formed in PVDF15 and the aggregates worsened in PVDF20, which would have resulted in regions with great amounts of antifouling copolymer units and regions wherein there are no antifouling copolymer units, these areas in PVDF15 and these areas in PVDF20. And this is why in both the bacterial cell attachment test, PVDF10 outperformed PVDF15 and 20, and it's also the same trend in protein adsorption test. This is why we use PVDF10 for the cyclic water bacterial filtration used to simulate the wastewater treatment, no? And these are the normalized flux that we calculated from 3 datasets. And as you could see, PVDF10 outperformed commercial hydrophilic PVDF when it came to the last cycle. We evaluated the membrane's performance. Rejection is at 100 for both. PVDF10 had greater flux, and it also has a greater flux recovery ratio. DRR stands for the decline ratio due to reversible fouling, and IR for irreversible fouling, where PVDF10 had had lesser irreversible fouling compared to commercial hydrophilic PVDF, which is probably the reason why PVDF10 outperformed commercial hydrophilic PVDF in the last cycle. And we also evaluated the stability of the membranes by GFP E. coli attachment test after 6-week immersion in the eye water and found that there is little difference from before and after 6-week immersion period, indicating that the coating is relatively stable. This is because of the entanglement of the copolymers to the porous structure of the membrane, thereby making it more stable, not compared to other coating mechanisms, which does not have this mechanism involved. In conclusion, after modification, the membranes had very high porosity of more than 75%, especially for PVDF10 and 15. Results from the FTIR and XPS analysis showed that although only one surface of the membrane was exposed to the spray, it managed to modify the bulk of the membrane. Static antifouling tests revealed that PVDF10, or a coating solution of 10 mg per ml, exhibited the best antifouling properties. Dynamic antifouling tests showed that PVDF10 outperformed commercial hydrophilic PVDF, and the stability of the membranes were relatively stable after 6-week immersion in the eye water. For further recommendations in the study, there is a limitation when it comes to using GVL because, again, if we didn't cast the casting solution immediately, it could gel, and this could pose us a problem when using additives such as vitrionic polymers in the casting solution. We further recommend exploring various parameters of spray coating such as spray pressure, distance from the nozzle to the substrate, or scan rate, and this will be necessary for further improvements of the membrane. Thank you so much for listening, and I hope you learned much from this presentation. Thank you again. I am Trisha Nicole M. Lazo, a BSMS Biological Engineering student under the supervision of my thesis advisor, Dr. Lemmuel.